I'm Eric Brynjolfsson, Director of the Initiative on the Digital Economy, and so delighted to have our speaker today. He has many titles, professor at NYU, one of the leading thinkers in the field of artificial intelligence, writer for New York Times and New Yorker and other publications, trade books, CEO, founder of companies, some of which he's already sold. And my favorite title is the one he's got in his bio here, AI Contrarian. And we'll hear today a little bit about his views and contrary views on artificial general intelligence and why aren't we there yet. Please welcome Gary Marcus.
Thank you. I feel a little scratchy, so I may not be able to shout. You can slide up if you can't hear me, I guess. So what am I contrary to? I guess it's the enthusiasm of Andrew Ng, among other things. So Andrew had a Harvard Business Review article late last year in which he said AI can do basically anything a person can do in a second. And I think if that were true, then Eric's mission to work on employment would be even vastly more urgent than it actually is, because we really wouldn't have a lot of jobs, because most of what we do in a second and then maybe accumulated periods. There are things we can actually do, or sorry, that machines can do that we can do in a second, like we can tell the difference between a with a golf ball in a second, and you can train deep learning systems to do that, and probably also to tell the difference between. Well, it gives a low probability. The numbers here aren't made up, but they're illustrative. And of course, the way we do this nowadays, we take big data in, and statistical approximations come out of the other end of what's typically a deep learning network, a convolutional network invented by my NYU colleague Jan LeCun. I'm going to assume people know roughly how they work, but you can ask questions if you like. But I think even on the narrow task that I just talked about, which is recognizing objects, that the reality is that deep learning still has a lot of problems. So the first is it requires a lot of data, and we have that for some things that we might want to recognize, but not all. Generalization can be pretty limited, and long tail cases often produce bizarre failures. I'll give you an example of that right now. So when you have something that's as dependent on big data as deep learning, the typical situation is there are things in the left-hand side of distribution for which you have a lot of data, the systems work very well, and as you go out into the long tail, they don't work as well. So here's another example of something you can do in a second. You can look at this picture and you can give me a description of it. You might, for example, say a group of young people playing a game of Frisbee, and Google actually created an AI system that was able to give captions like this. The New York Times reported it. People were like, AI is almost solved, like natural language is hard and image recognition is hard. Look, isn't this great? And we're just a couple years away. And here's another example, a person riding a motorcycle on a dirt road. Now here's a pop quiz. What's this? Apparently, if you are a machine, then you say that it is a refrigerator filled with lots of food and drinks. I don't know if anybody read Oliver Sacks' Man Who Mistook His Wife for a Hat. People who do this stuff for a living are like, oh, well, that's just an optical illusion. Jan LeCun told me that. I think this is more like a hallucination. We're not a little bit off. We're really not against it. Here's another example from some of the people that actually were at my last company. Actually, all of these people were at some point in my last company. So you see this, and if you're trained on the database for ImageNet, then you say it is a school bus. If you're a human being, you might say that's a pattern of stripes that's diagnostic of a school bus, but you don't think that pattern of stripes is a school bus. Or you look at this one and you say, I don't know, there's a bunch of dots or whatever you say. If you're trained on ImageNet, you can't really think outside the box, and so the nearest entry is a digital clock. Again, you would not mistake this for a digital clock. And what these systems do at best is perception of individual entities. They don't really understand scenes at all, and especially novel scenes. So if I show you this, and your deep learning system, you'll certainly get the barbell. That's like the most salient thing in the scene. You might get the dog, but I wouldn't be so sure of it. It's going to depend on the training regime. So another thing to know about these systems is they're very sensitive. What is the training data? The exact training data, if it's slightly different, you get different results. I think humans are much more robust across a variety of training regimes. So you guys have all had very different experience with dogs over your lives, but I'm guessing you can all recognize that dog, even with its ears in unusual position. But in any case, even if a deep learning system can correctly identify the components, it's not going to be able to do what you can do, is just to say, wow, that's really weird. A dog doing a bench press, how did it get so ripped that it could manage to hold that barbell, right? Deep learning systems can't make inferences like that. I didn't have time to put the actual video, but you go look on Wired. This came out yesterday, and I think it illustrates the point that there's no common sense behind the recognitions. So this is the iPhone X, I guess they call it, with its new face recognition system, which is, in part driven by deep learning and by modern AI techniques, and correctly identifies this woman as the owner of the iPhone. It, however, incorrectly identifies her son also as the owner of the iPhone. As part at the top, that's a bit problematic. The wife has to delete certain text they don't want the son to read because of this mistake in recognition. Well, of course, they share some facial features, but there are also cues that you can use because you have common sense reasoning to identify that this person is like the wrong size and possibly be the owner of the iPhone. And the systems are still pretty limited, pretty shallow. So here's Andrew's actual quote. He says, if a typical person can do a mental task with less than 1 second of thought, we can probably automate it using AI either now or in the near future. And here's my kind of not paraphrase, but reality check on it. If a typical person can do a mental task with less than 1 second of thought, and we can gather an enormous amount of directly relevant data, we have a fighting chance, so long as the test data aren't too terribly different from the training data, and the domain doesn't change too much over time. That's reality. I see someone taking a picture, I'll pause. So here's some of what we can do, and then some of what we can't. So in green, we can do speech recognition, especially in quiet rooms with speakers asking search queries, but not necessarily like in noisy cars asking things that aren't search queries. We can do image recognition in bounded worlds with limited numbers of objects, but not necessarily scenes. We can do natural language understanding in narrowly bounded domains like sports scores, but not more broadly. My son, who's 4.5 and follows in the family footsteps, likes to play with Alexa and try to get it to turn up the volume using alternative locutions. It's very easy to fool Alexa. Advertisement targeting, we're pretty good at, maybe not great, but doesn't matter. And then there are lots of things that we really can't do yet. So despite all the enthusiasm for AI, we can't really build anything like an open-ended conversational interface. I mean, Amazon is certainly racing with Apple and so forth to do it, but we're not very far along. Automated scientific discovery is something people have been talking about since the beginning of AI 60 years ago, but I would not say we've made substantial progress, except maybe in theorem proving. Automated medical diagnosis, everybody's running around trying to do this, but we probably all know what happened with Watson and its efforts at cancer and how MD Anderson pulled out because it really wasn't working. Automated scene comprehension for blind people. Facebook claims to be doing this, but it's really like naming the object, not tell you what's going on with the object in the scene.
So how is that different from what you showed with the picture? Is that basically what you showed with the Google pictures, that some of them gets right, some of them gets wrong?
Yeah, and I mean,
labels.
The stuff that I've seen from Facebook doesn't even go as far as that. I mean, probably because getting it to work at that level is hard. I don't know.
But I mean, automating scene comprehension for blind people. I mean, a lot of those, people playing frisbee or whatever, that is sort of partly there, isn't it? Or
well, it's partly there, but like you don't. I mean, here's another way of putting the point that I should have said before. We don't know how to use deep learning techniques to be robust. So we can use them. We can get good approximate results a bunch of the time, but we can't get them to be reliable. And so if you're going to have a advertisement recommendation system, it's going to make this point later, but I'll just make it now, that is 80% correct and 20% wrong, oh well, you sold somebody the wrong ad, they didn't click it. If you have scene comprehension, people are walking around relying on it, and it's correct like 4 out of 5 times, the fifth time might be a disaster. So probably, if I were Facebook, what I would do right now is to limit it to like the objects I'm really, really confident of. I wouldn't give wholesale scene comprehension because I would wind up in litigation, but I don't know for sure.
I mean, I'm sure that the point you're making, but 10 years ago, there's always this thing with AI. Once machines do it, it's easy. It doesn't count anymore. A lot of these things are fairly amazing from the perspective of the year 2000. And so, if that much progress has occurred in 50 years, won't these other trees fall soon?
Well, maybe. So I was talking to this man about Eliza in 1965. And I like to think, so Kurzweil talks about all the exponentials, right? And there have been exponentials. So transistors are, somebody can tell me, 10 orders of magnitude cheaper than when Weizenbaum was building Eliza in 1965. We have vastly more memory. We have vastly more computation. We have vastly more data. but on what Eliza was at least tongue-in-cheek pretending to do, open-ended conversational interface that you could talk to it about anything, I would say we have not made orders of magnitude increase. In fact, I would say Siri and Eliza are not that different. So I should have stressed the title more, which is about artificial general intelligence. We had a discussion about this over dinner. So there are a bunch of narrow engineering tasks that we can do well, like the ones on the left. I mean, these are the things that we can do now that we couldn't do 10 years ago. And then the things on the right, which I think are closer to what people talked about in the 1960s as their fantasies for what AI would do, on those things I don't think we've made that much progress. Machine comprehension may be among those the one that we've made the most progress because we can identify the objects, but there's still lots of problems there.
So if you mix it with the human, though, the total system makes it perform a lot better.
In some domains, I mean, it depends on your problem about whether that A is practical, B, whether the human has something to contribute, and so forth. So, you know, the paradigm example of this that people like to talk about is chess, where you know, the chess computers thought the humans are better, but as far as I know, that's not true anymore. So people, you know, are fixated on a short period in history in which there was profitable symbiosis. If you're looking at the long term, I'm not sure that will be true. In
It's
the
not
short
true
term,
anymore because now the machines are so much better.
yeah, the machines are so much better than the people that the people are just stragglers. It was like me working with Steven Pinker on my first journal article. Like I was in the room, but
It could be a busy street, or it could be a fridge. You might say, all right, well, I'm going to do street.
well, there's a couple things in there. So one is you can use the priors, your prior knowledge to constrain what your guesses are, and you know people are trying to do that in the car domain. I would say that the state of the art in AI is that we're not that good at integrating things like priors with things like deep learning. So deep learning is almost entirely knowledge free. There are people working on Bayesian approaches, for example. One of the best people in the world at that is Josh Tenenbaum here. But there's so far mostly separate paths, and I think there's a lot of work to be done to integrate those paths. Something I'm very interested in, but it's not there yet. And then the other piece of the answer to your question is like, if you're talking about something that has to be done in real time, like driving or maybe seeing comprehension for blind people, then you can't rely on the offline help. If you are running Facebook's news feed and you want to, find objectionable content, then maybe you can have people do some of that offline. It doesn't have to be all done simultaneously, and then it becomes more possible. So that's the problem.
I'm interested in hearing a little more about Andy Anderson pulling out of the Watson program. And the reason I say that is because just last night I listened to a presentation where everyone was so excited about how Watson had been aware of all of the current clinical trials, all of the available medical literature, and was in a position to uniquely sort through what might be relevant versus what was not, to allow people to actually focus in on a much smaller subset of information as opposed to quote unquote automating an actual diagnosis.
I mean, that's what IBM's marketing people said. You can look it up offline. And MD Anderson, Cancer, Watson, there was an expose of this about 6 months ago. The bottom line is it didn't really work that well. There also wasn't a lot of data collected to show that it worked well. Actually, I'll say one more thing. The fundamental problem there is Watson really is an information retrieval system like Google. It's was very tuned to Jeopardy. But it's not an inference system. So Watson doesn't really reason. And a lot of what you want to know in medicine isn't necessarily spelled out on the page, especially if you're like trying to understand how to treat a rare disease or a disease that's only just been discovered, something like that. And the answer is not on the page. You have to make inference. And this is the general problem with machine reading, is that some of what we care about is on the page and some of it's not. If I tell you I'm going to ride my bicycle from Seattle to Vancouver, I don't tell you that I'm not going to fly, I'm not going to ride underwater. I don't tell you that I'm not going to, go all the way out of my way to Montreal in order to get there. You know a lot of things, common sense things about the world, and you recover them even though they're not stated anywhere on the text. And the state of the art is we don't have a system that can do that.
Well, I have trouble with the words out of reach. This kind of
Out of reach. Where do I have out of reach?
top.
Oh,
But it's sort of black and white, green and red.
Yeah.
It's green or red. And whether you mean out of reach this very moment or 5 years, 10 years. You take medical
I mean that right now these things are not.
Very well.
I mean, on this particular slide, I'm just kind of telling you the state right now.
Well, maybe
I'm going to talk in a few minutes about, and maybe I should go back to talking um, um, about what I think some of the obstacles are right now. I don't think any of them are insuperable in principle. I think that there's a sociological problem with the state of AI. I think people are looking at the wrong place. You know the old joke about the drunk is going around in circles looking for his keys, and finally somebody says, "Why are you going around in circles?" And the answer is, well, that's where the streetlights are. I think that there's a very big streetlight problem in machine learning right now, where people are pursuing too narrow set solutions. There's nothing in principle that says they can't pursue others. It's just sociology and time, maybe money. But I think, are these out of reach? Like AI is never going to do them, like Bert Dreyfus used to argue? No, I'm not making that argument at all. I think all of these things can be done, but I don't think they can be done now.
Should also, well, you say that diagnosis. My understanding is that now computers can better read an MRI. Do you have a rotator cuff issue or a?
I don't think that's really true. I think there are limited cases. There are demonstrations, for example, in radiology looking for tumors, but they're like pretty carefully selected data sets to show that machines can do this. As far as I know, nobody has really yet replaced radiologists. They will, but part of the problem there is there's also often a lot of unstructured text in the person's file that's relevant. And one way to think about it is there's not necessarily a one-to-one mapping between most measurements and most diseases. It's just not that simple. So you have single gene disorders. If you have this, I know you've got cystic fibrosis. But a lot of things, like I actually want to know all about the patient and not just look at this image. And at that point, the systems aren't that good. The cases where you really can do it straight from the image will be solved in the next couple of years.
Or I mean, we should let you go, but just on that point, there was Sebastian Feinstein wrote an article in Nature earlier this year where they compared a set of board-certified dermatologists to a machine learning system, and the machine learning system did as well or better at that very narrow image recognition task.
That's right. And I mean, that's the way it will unfold, is first on very narrow tasks where you can constrain it so you don't need to know a lot of prior things. You just need to be able to read it off the image. That's where you will see progress first. And then safe, reliable driverless cars is the last thing on the slide. It's an open question whether the methodologies people are using to make driverless cars now are actually at the safety levels we need. I'll come back to that in a second. So the way I see it in general is the cognition, which is what I studied when I was a Pinker student across the street, is made up of a lot of things. You have perception, you have planning, you have common sense, analogy, reasoning, language, etc. And the progress that we made primarily, almost exclusively on the perception side. So we're pretty good now at doing the low-level perception that your occipital cortex does. Maybe not everything your occipital cortex does, but at least recognizing different textures and so forth, we're pretty good at, and you can use that and apply it in a lot of interesting ways. But that doesn't mean that we sort of have a general understanding of how to build intelligence in a machine. My biggest fear about AI is not Skynet, although you should all watch Stuart Russell's thing about drones. If you haven't already, you can look at my Twitter for 8 minutes about the future of autonomous weapons, MIT or whatever, at Gary Marcus. I tweeted you the link a couple of days ago. That's pretty scary, but I'm not talking about it today. My biggest fear is actually we're going to get stuck. So a big metaphor in the deep learning world is about gradient descent. You're trying to get to the bottom of some mountain. I might have this upside down. No. You're trying to get to some bottom of some mountain, and you take small steps. Try to always go down, never go back up. And the problem with you follow that strategy is maybe you're over here and you want to be over here. And actually, I've been showing this graph for about 6 months. Lately, people in deep learning, the people I'm criticizing, have been saying, we haven't figured out anything new this year. Right? So they actually have a sense. Like if you look up in Quora what happened in 2017, the people in the field, I think I had a slide actually from Jeff Hinton later. The people in the field actually are maybe starting to realize that this might be the case. This would be a shame. I assume in this crowd, I don't really need to make the positive case for microbursts on AI, but we would like machines that can read, that can cure cancer, like robots that can take care of our kids and our sisters and so forth. If we got stuck, we wouldn't get to do any of that. We're not there yet. There's plenty of room in principle we can advance to AI. But at the moment, I'm not sure we're going there. So you can actually think of the whole field as doing gradient descent through the space of possible models and doing really, really well on object recognition. Maybe we're actually at the theoretical limit. for how you can distinguish two breeds of dogs. So machines can do this better than people up to a certain constraint. Same thing with speech recognition. I mean, speech recognition is not really better than people because people know more about language. But if you take isolated syllables outside of context, the machines are basically as good as people. Language translation, not really as good as people, but it's phenomenally good for what you can get for free on Google Translate. Doug Hofstadter has a neat piece that's coming out about language translation and why it's still not as good as people might think, but there's obviously progress there. But there are other things like natural language understanding where I think this local minimum notion might be totally right. So people have been using deep learning in natural language understanding, and it's really not very good. There was a paper by Percy Lang that I should be citing up here earlier this year that showed that you can fool these systems just by adding embedded clauses. So you have, the rat chased the cat and it's fine, and then you say the rat that happened on this day to look nice, blah, 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 and the systems can't do it anymore. So you just add like distractor words, and they don't really work. There's something fundamental that is being missed in natural language understanding. So the fundamental risk is researchers can spend a lot of time on a task only to hit a wall. If you're stuck in a local minimum, that's to say that you've reached an asymptote, and that can be fine in some places. So it's tolerable for recommendation engines. If I recommend to you 19 songs that you like and you don't like 20 songs, nobody cares, right? And just say, well, I was trying to mix it up a little bit. It's fine. But if I do that for a pedestrian detector, I'm correct 97.5% of the time because this technology is doing approximations without really representing the underlying phenomenon about what a pedestrian is, well, that's not fine, right? And you scale that out to 1 million cars in your autonomous vehicle fleet, and the newspapers will be nothing but reports of unintended deaths. Or if you have a domestic robot doing elder care, and it lifts grandpa into bed 39 times out of 40 and only drops him once. All right, so why aren't we there yet? So here's what I think some of the obstacles are. The first is the dominant paradigm right now, which is indeed important, we shouldn't be dismissing, is machine learning. Machine learning is not something we really know how to engineer well. So you can compare it to classical computer programming. I imagine probably at least half of the people in this room have done that. You start by building little modules, and then you build bigger modules out of the little modules once you know the little modules work. Deep learning is actually kind of pushing in the opposite direction. People talk about end-to-end deep learning. I have my inputs, I have my outputs, and there's no prior structure in between. Well, that means there's nothing you can debug in between either. People do end-to-end learning for video games now, for example. So the input is pixels, and the output is where I should move my joystick. And when it works, it looks great, but it doesn't always work. So there's some great demos. I'm referring, of course, to the Atari game system that DeepMind made very popular. Well, it turns out you can break it in all sorts of ways. So, for example, Vicarious, a company in California, it's mostly been in stealth mode, had a paper earlier this year where they showed that if you change the intensity of the pixels in game breakout, the whole system just falls apart and looks as if it has no idea what breakout is anymore. Well, how do you debug that in a system like this? It's not clear. There's no module that does the perception of the bricks. And so it's not clear how you fix it. So they're difficult to provide credentially, they're difficult to verify. So it's very difficult to get anything like a proof out of how deep learning works. Peter Norvig gave this great talk 2 years ago on at MTech. I was at the same session, and I think this is online. And he gave an example like, well, you know that these things work on Tuesdays, and you know that they work on Thursdays, because you tried them on Tuesdays and Thursdays, and then a holiday comes, and you have like no idea whether it's going to work anymore, because you don't understand the underlying principles. So we actually have no procedures. It's not just deep learning. We have no procedures so far for reliably building complex cognitive systems. We don't have a methodology to do it. So in the driverless car industry, what people are doing right now is they're like, well, it doesn't quite work well enough because some people died. Well, at least one person died. I've seen claims of another. I'm not unconfirmed. Certainly a bit accident. And so we know it doesn't work. What are we going to do? And the methodology is let's get more data. But we don't have any proof that as you get, how much data you would need in order to deal with all the outlier cases, right? The problem with the driverless cars is you have things that are unpredictable. So it's easy. I'll take your question in a second. It's easy to collect data of sunny days on highways, and mostly that works out pretty well. But people don't have as much data about rainy days or whatever. We don't have formal proofs that we are going to be able to collect enough data to use this kind of report approach that people are using.
So, well, we don't have any proof we have enough data to make it perfect, but is that
Or
is that the standard?
99.99999% accurate. Or
Is
something like that.
99.999% accurate, or is it
And people in the field talk about 5 or 6 nines.
But doesn't, like you said, it depends on the application. If it's recommendations for cars,
For recommendations, it's fine. It
we
doesn't
know
need to
that
be any better.
with cars, thousands of humans to kill other humans
That's right.
with driving cars. So if it were
This
90% better than that, would that be worth implementing? But not perfect.
Would it, if it's 99% correct or 99%
No,
or 99 times better?
suppose it goes from 30,000 deaths to 3,000 deaths. 3,000 deaths is a lot of deaths, but
I mean,
I don't,
I'm all for it. If we can cut the death rate by 90%, I think that's great. But like the numbers that we've actually quoted, like Elon Musk says, well, we drove 130 million miles, we only have, 1 fatality. But it's not a fair comparison because it's actually human assisted, if you want to call it driving. And only occasionally is someone foolish enough to watch Harry Potter in the backseat. We don't have the right denominator there.
I actually think it's quite able to lower the death rate and still have a lot of deaths that you survive. Like
There's that.
The cars, it works great in most situations, but every once in a while just drive off a bridge for no reason. Your probability of fatality is still much lower, but it will be for the wrong reasons.
Yeah, there's a whole set of legal and social issues I don't want to go into right now, but I agree with you. I mean, whether or not society gets to driverless cars that save lots of lives depends on things like that. So, the first accident that involves a school bus or something like that could derail the whole thing, even if statistically it's better. But I want to focus on the kind of technical side for right now. So there's another great paper came out of Google called Machine Learning, the High Interest Credit Card of Technical Debt. I don't know if you guys all know the term technical debt or you don't. Technical debt is like, I build this thing, it works on Tuesdays, but I don't really know if it's going to work on Thursdays. And Thursday comes around, and it turns out my product description is a little different from the one before, and I need to rewrite everything from scratch. So like, I'm holding it together with Band-Aids in order to have the demo, in order to, get my journal article out or whatever, but it doesn't mean that it's really sound. So it's not just me coming from the outside. People who are on the inside of the field are pretty worried about this. And there's this great cartoon from XKCD that I think really captures the state of the field right now. One guy says to the other, this is your machine learning system. And I guess she says, yeah, you pour the data into this big pile of linear algebra and you collect answers on the other side. That's basically what machine learning is right now, is big piles of linear algebra. And the first person says, what if the answers are wrong? And the second one says, well, you just stir the pile until things start looking right. And that kind of gets you so far. Like, it works for the product you're building now, but the way Leon Batu put it, he's at Facebook, used to be at Microsoft, is if you want to build services in a complex system, that's really risky because you don't really know if that mix is going to work when somebody else in your company tries to use your service for something else. So you made it for you made it for image recognition on the assumption that there were only 10,000 categories. Now the next person tries to do it where there are 100,000 categories, maybe it doesn't work anymore. And you don't have the trustworthiness that you do for like a printing service, where if I send this off to my printer, I know it's going to work.
Is that true for sort of industrial applications as well as research? Are the algorithms the same? Is there technical debt?
Yeah, it is the same stuff.
It's the same stuff.
I mean, there's always a question of like what's unknown out there, but like the best one can tell from talking to people at conferences and seeing what they publish and so forth, it's not like Google has some secret sauce here. It's very competitive. They all want to win these ImageNet competitions, for example. Even though they don't necessarily get money out of it, they get more talent and so forth. So I don't think anybody is kind of holding the secret to AGI and hasn't told anybody. It's not impossible that like Vladimir Putin hasn't. He's about to take over the world, and
I'm
but
just thinking Nuance is a good example. Speech has been
Nuance is not.
It's not.
I mean, yeah.
The technical debt specifically. I'm just thinking about industrial apps that have been out there for 10 or 20 years.
I mean, certainly Nuance has a handle on how to work on the problems within the constraints of what they do, but they work on pretty constrained versions. So they make a lot of their money from doing medical transcription, and they have massive databases for that stuff. And they know that if they translate it into another language or something, they've got to go out and collect another huge database. And they have at least a little bit of methodology there, but it's a methodology to do the problem itself in as constrained way as possible. Second issue is that statistics is not the same thing as knowledge. The field is obsessed right now with statistics, and I'm not like morally opposed to statistics, but I don't think that capturing everything with big data is the right way to go. So I had an article with Ernie Davis in the Communications of the ACM, and we didn't make the cover, but our piece was on the cover. And there's this great illustration there of a robot with a chainsaw on a tree. And if you look carefully, you will see if the robot keeps going with that chainsaw, the branch and the robot are going to fall. Well, you don't want to train this with deep reinforcement learning, right? So deep reinforcement learning is what DeepMind made famous with the targeting system. The problem is it requires millions of trials in a world that you can perfectly simulate. Well, you can't perfectly simulate the world of trees, and you can't have your robots fall a million times and kill pedestrians. Well, it's not practical. And so you could try to solve any given common sense problem by having massive amounts of data if you could perfectly simulate the world, but we can't really do that. We probably really need more abstract knowledge, and people are not really even thinking about that question in those terms.
Are you going to talk more about simulating things like the AlphaGo Zero and how
I'll talk about AlphaGo Zero.
What other things you might be able to simulate? Games, obviously.
Not so many, but we'll come back to it if I don't answer it.
Okay.
I'll just give you one example of content. So I can ask you, can a spider get out of this jar? And I could give you some training examples, and you could learn that the jar is closed, the spider can't come out. But once you learn that, you can pretty quickly figure out, like, okay, this is a different kind of jar, and I could play tricks, we could have magic tricks. But in general, you could look at these and you say, yeah, the spider is going to be stuck in here, and the spider is not going to be stuck in here. I wish I had a better image, but the spider's probably going to be able to get out of this one, and the spider's probably going to get out of that one. And you have intuitions about, this one will work, but you better put the cover on that one if you want to keep the spider. So you can do all that reasoning. You don't need that much personal experience with spiders and jars. Probably most of us don't want that kind of personal experience, but you can make the inferences, right? This is what I mean by common sense. Or you look at this. I never heard of this thing, and I've already forgotten the name of it. It's like a yarn feeder or something like that. I tell you that once, and you get it, right? Even if you don't knit, you kind of get the general idea, and then it doesn't have to look the same. It doesn't even have to look very nice, but you can tell this belongs to the same category and so forth. So this is what I mean by common sense reasoning. Like you can recognize a new category of what it allows you to do, all this kind of stuff, more or less instantaneously without billions of training examples. The third problem, I think, with the field. So the second problem is nobody's even reckoning with this question of common sense, just to close the last one. So they're not even thinking about how do I build systems that do this kind of stuff. They're focused on maybe how I recognize a label on this, but that's not the same thing as how do I reason about it. So there's a lack of attention even to the problem. The third problem is there's a huge bias in the AI field to just assume that everything is learned and nothing is innate. And if there's anything I learned here at MIT in the kind of orbit of Noam Chomsky and Steve Pinker, both of whom are no longer full-time employees at the university, it's that maybe there's actually some innate stuff. There's something built in. At least in biology, I think that's absolutely clear. I mean, there are some people who disagree, but I think that there's no basis for it. People in machine learning are like, well, we just need to learn stuff. So we'll have more data, we'll watch a bunch of videos, we'll learn what we need. They literally don't want there to be more innate structure. Pinker, in his classic book, The Language Instinct, which he wrote when he was still here, laid out a bunch of arguments, many borrowed from Chomsky, for why we might think that there are innate things in human beings. In the interest of time, I think I won't go over those now unless you ask me to. I think there are strong arguments for thinking, I'll just do the first one, the poverty of the stimulus argument, which is the ability to generalize seems to go far beyond the data. So, you might hear a billion sentences like you can understand an infinite number of sentences. For a kid, you've only heard millions, and still you can essentially understand the number of sentences. And that was in the 90s when I was in graduate school, but the data keeps coming in. So somebody just showed that late-term fetuses, like the one came to dinner with us last night, can distinguish between. We had a dinner guest who was 8.9 months pregnant, who's not here. And a fetus like that can distinguish between a face, I don't know if I have a laser pointer, and an inverted face. Like, before you can plausibly say there was any input data that possibly could have taught them that. And then you look at developmental neuroscience, and there are amazing studies like this one, where synaptic transmission was literally cut off in mouse embryos. And still their brains, to at least the first approximation, you can't actually tell which of these columns is the normal mouse and which one is the knockout mouse that doesn't have synaptic transmission. Now, I'm not saying that organisms don't learn, or they don't have plasticity, or they don't recalibrate, or anything like that, all of which would be absurd. But what I am saying is there's lots of reasons to think in biology that the basic structure of our brain comes from our genome, and that the genome is basically an autonomous factory for building brains. I don't know if I have these data here yet. Almost all of the genome is expressed in the brain. A lot of it's expressed selectively in parts of the brain. Yeah, Ellen, Brain Institute is going to have some data about this coming out in a couple of weeks. It's just overwhelming, in my view, in neuroscience that there's innate structure. I'll skip that one for now. So the view from biology, which I wrote about in a book called The Birth of the Mind, 2004, which I basically stand by, is that pre-wiring doesn't preclude rewiring. You have both kinds of processes in biology, just like you can build an arm and then you have regenerative processes if you injure your arm. But there's just a ton of evidence for innateness. Okay, so John Locke saying you learn everything from experience, wrong for biology. But the paradigm in machine learning is to just ignore all of that. It's to say, well, let's go learn this. And so you have people like Jan, who is my friend and colleague and friend of me at NYU, and we had a debate a couple weeks ago about innateness. And I quote from Tech Review. He says, so human children are very quick at learning human dialogue and learning common sense about the world. So he is acknowledging my common sense point. But then he gets the solution, and he says, well, it's some learning paradigm that we haven't figured out. Well, that's possible. It's a learning paradigm that we haven't figured out. But it's also possible that we need some innate structure, or both. Before we had this debate, the philosopher David Chalmers, who convened the debate, was like, what are we going to debate about? And Jan actually suggested innateness. And David did a Google search that he reported back to us. He said, when I do a Google search on nativism and AI, I get a do you mean message. Did you mean message. Like, people don't even talk about the question. So I kind of already said this one. We might need better algorithms, better learning algorithms to get to that next generation AI, but we might also need more machinery constraining what those algorithms require, or more likely, we actually need both. And an aspect on A that turns out to be important is that learning algorithms themselves are innate. So you can put anything into the learning algorithm by making it complicated enough, and we'll see an example of that. I think this is actually an aesthetic. It's an aesthetic that I would call physics envy, which is people in the field that I work in, neuroscience, cognitive science, AI, all wish it was like physics where you could have your answer in 4 equations on a t-shirt. Well, that would be nice, but I don't think biology works that way. So biology is a lot of mixture of chance over time and so forth. The solutions just aren't as clean as all that. Here's an interesting thing that came out from DeepMind, right? DeepMind has, the best Go player of all time. Now they have the even better Go player of all time. And they go working on language, which is the domain that Pinker and Chomsky work on, and they really don't do so well. So they have something in a virtual world using reinforcement learning, and it tries to find the green object and that kind of stuff using what's basically kind of a standard deep learning approach. And they find that it can learn a few words, but if you look at the x-axis, which they make it easy for you, if you look at the x-axis, it's taking like 500,000 trials to learn one word. You compare this to people, and it's absurd. Susan Carey, who was also here at MIT at one point, who was on my thesis committee, had a famous paper showing that you could ask a child, bring me the beige one, not the blue one. And in one trial, a kid figured out that was a color word. Maybe they didn't figure out exactly the boundaries of beige, but they could use reasoning and so forth. A single trial, they know it's a color word and have some idea what it is. This is very far from the results that DeepMind can get. When they take their Go techniques, I'll take your question in 1 second, it's very far from when they take the Go techniques and apply it in language. They didn't put this in the paper, but I watched them give a talk. What happens if you do negation, like stay away from the fridge? They just had atrocious performance. They didn't want to put it in because it was so bad. So they go really, really far from what a human child can do when they transport this. And this is a partial answer to your question. It doesn't work for things like language. Your question. I think I have about 7 different things there. I'll try to I think it's a good question, a set of questions. So first of all, the sheer number of neurons I don't think makes that much difference. So what happens is you increase the number of neurons in a system like this is you tend to overfit. So you learn a specific training example that doesn't really help you with general data. Google is not lacking for computational resources. They're not some teenager in the basement. If they want more resources, they can do it. Everything that they publish, they've done a lot of hyperparameter search and so forth to figure out what's optimal for that problem, including running big models. So I don't think that per se is the right answer. The broader question that you're asking is really like opens into the question like what counts as the same system or a different system. So in principle, a neural network, the brain is a kind of neural network. I can build computers out of neural networks. So I can build a Turing machine out of nodes in a neural network. And the real question is like, what is the nature of the system that you need in order for a system to work right? So I could take one of these things called AutoNL, look for models automatically, and the real question would be like, what does it map onto? What are the hypotheses that are actually being embodied in this network? So the kind of thing that they're trying to test right now is that you can use pure reinforcement learning without prior knowledge in order to solve the problem. Could turn out when you do this search, which is kind of like evolution, that the only models that actually work are ones that have pure reinforcement learning working on much richer models with built-in tree structure and hierarchical compositional mechanisms and so forth. And then you've just gotten to the same solution that Noam Chomsky would want you to play. Labeled as a different thing, but the essence of what makes it work, the one maps onto the other. That's what I think will actually happen when using data science.
So maybe you and agree that like you're saying innate possible neural network structure that we have to resolve evolutionary problems, and we just really bad at figuring out what that thing could be.
I mean, in terms of Jan LeCun, he's no longer a straw man because we had this debate. I know what he would say, and we really do disagree.
And there's a video of this, by the way.
There's a video of this. You should all watch this video if you find this conversation today. It's really a great debate. I've been in two great debates in my life. One was with Josh Tenenbaum that was at Harvard. That's online as well. It's really worth watching if you care about these issues. But so at a crucial moment in the debate, earlier debate, I presented a list of 10 things. I think I have a slide on it here that I thought were innate. And Chalmers said to LeCun, so which of these 10 do you think we really need? And one of them was actually translational invariance, so recognizing the object is the same object in different places. And as I pointed out in an earlier point in the debate, the best way to do that was actually invented by Jan, and that's what a convolutional network is. So that was on the list. And Jan's answer was none of the 10. We don't even need the one that I invented. So we have a real difference. It's not a straw man when I say that at least some eminent people in machine learning want to have none. He said it in the debate, so you can watch it. I think I have the list, and if I don't, let me show it to you later. I sometimes show this video. I'll just show it quickly because people never believe there's anything innate in humans. So I show them baby ibex climbing down a mountain. Baby ibex climbing down a mountain cannot do trial and error learning. Evolution can shape the brain structure so that it knows, what climbing is and something about surfaces and so forth. That must be what is going on. There has to be an structure there, and you can contrast this with the creatures that Eric has in the office. And even when you train them in simulation and everybody knows exactly in advance what they're going to have to do, as they did in the DARPA competition a couple of years ago. People take their empiricists learning things and then they put them out in the world where there's gravity and wind, and they just don't work that well. So here's, don't take my word for it. Take Jeff Hinton's word, right? He's the most famous person in the deep learning world, and he, who I think hates my guts, is probably fair to say, has kind of come around to my position. He, at least in part, he said that maybe backpropagation, which is what drives deep learning, is not actually the right way to go. So you can see this interview with him in August or so, or September 15th. On Axios. People have been parsing it like the Talmud, trying to figure out what did Jeff exactly mean by that and so forth. I think I have a comment for a second, and I do indeed, which is Jeff probably means something different than I do. We both think we need to look somewhere else. He thinks we should look at unsupervised learning, and so does LeCun. So I want to say a little bit about that. There's a lot of talk about it. So there's a few different ways you could think about unsupervised learning. One is, well, what if I show you a lot of pictures? I label them, but they have some commonality. The famous Google cat detector system was a version of this. The idea is you cluster similar points together without any prior knowledge. So this is an active area of interest in unsupervised learning. I think people need to do some work there, but I don't think it's the salvation. And then there's Jan LeCun's version, which is a very interesting version, which says the problem with supervised learning, I didn't really use the term today, is you need a lot of labeled data. So you pay a bunch of people on Amazon Turk or something like that to label and say this is a bottle and this is a knife and this is a fork, and you have to pay them a lot and they don't pay much attention. And there's never going to be enough. So LeCun at least has acknowledged for a while that that's not really a viable way to get us all the way to AGI. So he says, making the following clever observation, he's not the first person to make it, but video is a great training signal because the world is relatively stable. There's a great old paper by Peter Polyak that made the same observation. Because one frame is likely to predict the next pretty well, you can learn a lot. So for example, if you were watching, I mean, first of all, many things are stable. So, you know, if the wind's not blowing too much, then your leaves are stable. And sorry, you can't see it that well, but if somebody's riding a bicycle, you know, you can predict where the pedals are going to be at frame 7 by looking at frames 1 through 6. So it's a very powerful supervisory signal that comes very cheap because you've got lots of YouTube videos. So this is what he means by unsupervised learning. I don't think it's going to work. I mean, it can work in limited domains, but I like my friend Eric Michelli, who I think is the only Emmy Award-winning computational neuroscientist, what he said about this, which is you can't model the probability distribution for the whole world because the world is too complicated. So, I mean, it's an open research question, but I think that Jan is being naive about how complex the problem is of doing all of this prediction if you're going to do it straight from pixels or something like that. This is a demo of something that my last company did. It's kind of like the breakout demo I mentioned before. This is, again, using the Atari game system of DeepMind. You train it up on a video game, and it looks like it's doing great. You know, it avoids the obstacles, and you might, if you were DeepMind, put out a video saying, look how well we have learned to have a vehicle fly between the posts. But DeepMind never does what any good scientist would do, which is to say, well, how robust is that? Can you transfer the knowledge? So we did that at my company, and we moved the posts around, and you can see that the solution was not very robust. My concern about unsupervised learning is basically the same as my concern about deep reinforcement learning, which is if you do these things from pixels, the world is too complicated, you don't get to high enough level of abstraction, you never really get what you need. When I think about unsupervised learning, I think about my daughter, Chloe, who's 3.5, and we were in Vancouver over the summer. We were at a Whole Foods. This is, I should say, a reenactment, the second time that she did this. I didn't have to do it the first time, but I made her do it again. And so they had these chairs, and she looked at that chair, and as 3.5-year-olds are wont to do, she thought to herself, I think, you know, putting words in her mouth, you know, what's a cool thing I can do here? And she decided that climbing through the chair was a cool thing to do. And so she tried it, and it didn't quite work. She got stuck, and then she did a little problem solving, and then eventually she got her way through. This is what I think of as the unsupervised learning we actually need to do. It has nothing to do with the kind of technical techniques that the field is working on. It has to do with like an entirely different level of cognition. Unsupervised learning, the way that people do it in machine learning, isn't about these things. It's about forming goals, plans, determining what my body affords, understanding physics, problem solving, and so forth. I think if we can do the kind of unsupervised learning that Chloe was doing there, we will come a long way. But I think right now we don't have the right vocabulary of AI techniques.
Say more about, well, maybe you don't have the say more about why it's not about forming goals. Or, I mean, it sounds like she thought, okay, here's something interesting I can do, and made a plan to do it, and then
it's partly an abstraction
solved
level.
the problem of how to do it.
So, I mean, I don't know. I haven't done careful experiments on Chloe, at least in this regard.
I bet you have.
But I'm going to guess that, for example, she didn't represent this aperture at the level of pixels, but that she had a more abstract level of aperture. Same thing with her body. I don't think that it's kind of pixelized representation. I think it's more metric. I think she thought in terms of goals, like how do I get my hand through? And in general, the systems that we have today are like, what arrow direction do I move my joystick in order to maximize points from pixels? And it's just an entirely different level of abstraction. That's why it fails on the things that I'm talking about.
Different level of abstraction. We go back to that list. I mean, it looks to me like she had a goal and she made a plan and she solved a problem.
That's what she did.
Yeah.
And what I'm saying is we don't know how to do that with the AI system. So we don't really know how to even
Oh, I see.
We
Okay,
don't.
I see.
I may have confused you with the negations. I would say
I got
what
you.
we want. This
You
doesn't
want
really
those
work.
things.
What I want is for my hand to occlude the words, but it doesn't really.
Gotcha.
But if I could occlude those words for you, I would say that what we want are systems that form goals and plans,
Okay.
determine affordances. That's a technical psychological term for like
Gotcha.
what can I do with a
So
tool or my
the solution is, okay, yeah, the negation got me.
So
Okay.
these are, yeah, and I said it in a confusing way. These are the things that AI doesn't do now that Chloe does do are the ones that
Okay.
So another point I wanted to make is lots of models already have all kinds of things. It's never very principled. So here's the first AlphaGo paper in Nature. Nature seems to collect these things. It looks a lot like a deep learning system, and Demis went on saying there's no handcrafted rules here and so forth. But then you looked in the appendix. Of course, there's a newer paper I'll talk about in a second. But you look in the appendix, there was all kinds of crazy innate stuff, like how many opponent stones will be captured if I played my move here. So it was actually a lot of external symbolic systems doing innate stuff, and so there was innate stuff there that people just weren't talking about it. So the point I was making is sometimes the innate stuff actually helps you, and then the other thing that was vitally innate there was Monte Carlo tree search. So Monte Carlo tree search, I'm not sure if it was invented for Go, but it's something that's been very central to the practice of building Go systems. So nobody has built a Go system of any value in the last 15 years without using it. It's an extension of tree search, which is one of the first techniques anybody using AI for anything. It's equivalent to you playing chess and saying, if I go there, you go there, or you could go there, and I calculate out all the possibilities. Critically, it's tree search, which is to say it uses trees, which is what Chomsky has been pushing as the most central thing that is innate to language, and they had that innate there. So then, when I was talking in the debate with Jan, I talked about all the other ways you can build in innate stuff. So you can choose how many layers you have, what you do with the layers, what the activity function should be. I mean, these are all sort of the parameters of what linear algebra you're going to do. So there's lots of ways you can actually build an innate structure. It's just that nobody ever talks about it systematically. They do it anyway. And then came this paper a couple of weeks ago, which on its face was like a complete refutation of everything I have to say, because they say they mastered the game of Go without human knowledge. What I don't understand is the reviewers on this paper. It was published in Nature, which is supposed to have high standards, but they slipped in a lot. The first thing that should have been a clue is if you look at the 17 authors on this paper, 10 of them work on the last world champion Go system. It's not as if they were naive to the problem of how do you build a Go computer. And one of them, somewhere over here, was actually the European Go champion that they themselves beat. So they have some expertise. And they're saying that they started tabula rasa. Well, what you would want to know is that true? And if it's true, what are the implications? And they didn't really look. I don't know if I have enough. I do. So they actually built in the Monte Carlo tree search, which is, again, the first thing that Pinker or Chomsky or I would say you need to build in. So there's a version of this paper that one could hypothetically imagine, which is you would start with general purpose reinforcement learning algorithms. Show that you could use them for a lot of things. And say, well, we so happened to try it on Go, and it actually learned how to do Monte Carlo tree search. If they did that, I would bow down to them. There's a problem known in the psychological and AI community about representation learning. If they could learn the representation of tree search, that would have been a brilliant, amazing discovery. But it's not actually. They built in the tree search. They built in certain things in it, so they had humans augmenting the data because they noticed that the board is identical under reflection and rotation. They didn't have the system learn that. They built in a custom sampler in the Monte Carlo tree search. They say it's to work faster, but they didn't actually do it. You have to think when they do as much behind the scenes hyperparameter search and fiddling around as they do. Like, I've met interns that did this parameter and did parameter sweeps and stuff like that. They actually needed all of this stuff. And then you look through the architecture, they build in spatiotemporal invariance in very precise, bespoke ways. And then most importantly, they didn't actually show you could use the same system unaltered on another problem. That's the only way their argument actually goes through, is that they say, and then we took this system without changing a thing, without human knowledge, because that's the claim of the papers, without human knowledge, and we did something else with it. They did not do that. And so in my view, the paper should not have been published with that title or that claim. So it's still an interesting paper. It's a masterpiece of engineering. It's really great engineering. but it doesn't actually show you don't need innate structure. It shows that if you have the right pieces of innate structure, you can do really well. So what I think we ought to be doing is going after innateness in a more principled way. And I refer to Liz Belke, another of the great nativists who used to be at MIT, who says basically you need to build in things like objects, sets, persons, and places. If you start by having those kinds of concepts, you can learn about the rest. If you know Kant's critique of pure reason, this is basically a psychological version of what he said philosophically, where, at least as I interpret him, he said you need to be born with notions like space and time, and then you can start from there. So I think, yeah, this is the list that I discussed with Jan. I said these are the things that I think need to be innate. I don't know that this is my final list, but I can, for the purposes of the debate. Representations of objects, structured algebraic representations, which I talked about in my 2001 MIT Press book, The Algebraic Mind. All of these, or well, at least these, come from the arguments that I developed in that book that are applicable. And then some of these others come from Spelke's work from cognitive development. So I try to argue you need these things as your basis set. If you have that, then maybe you can learn richer things about how the world works. But if your basis set is pixels and joystick directions, I'm not sure how far you can go. And then, of course, Jan said, we don't need any of them. So we need to decide for ourselves. It's ultimately kind of an empirical question. So it could be that biology builds in all of these. We don't even know that, but the strong arguments where it's not proven. Could be biology needs all of these, and you just have a big enough data set you don't need. So it's an open empirical question about AI. Can you build your AI without them? How far do you get? And so forth. My view, I think, is pretty clear. I wrote in 2012 a critique of deep learning. It somehow made it to the most emailed list on the New Yorker, much to my astonishment. I said this: realistically, deep learning is only part of the larger challenge of building intelligent machines. Such techniques lack ways of representing causal relationships, are likely to face challenges acquiring abstract ideas. They have no obvious ways of performing logical inferences, and they're also still a long way from integrating abstract knowledge. It was almost exactly 5 years ago. One way to look at it is Marcus wrote this really negative piece about deep learning in the New Yorker, and there's been huge progress in the field in 5 years since. People have spent many billions of dollars. There's been exponentially increasing numbers of publications involving deep learning, and Marcus is totally wrong. But the other way to look at it is the things that Marcus said they're not going to be able to do, they still really haven't done. So machine learning is great. I don't mean to say we should stop doing it, but doing deep reinforcement learning, as DeepMind is making very popular, purely from pixels, is not really getting us closer to artificial general intelligence. If you can't tell that the posts have moved in your video game, you're not really understanding the world. We also need to have knowledge in our systems. You need to know what a post is, what an obstacle is, what a person is, what an object is. So we need strong starting points, rich representations of time, space, action, object. That's going to take it at a different place. Maybe they'll take it to a place that finally starts to look like AGI. I think that's it. Thank you very much.
Thank you, Gary. Let me take prerogative to ask a question about that last thing. So
Sure.
the examples you gave of what DeepMind was doing, I find very compelling and interesting, but a way of interpreting part of what you described is that we need more structure, but these guys actually put too much structure in there. But aren't they moving in the right direction in the sense that they had a lot of very detailed structure, and now the structure that they're putting in is somewhat more abstract, but there's still structure there. I mean, on one hand, you're critiquing them for having that structure in there, on the other hand, you're saying they should have more structure. So help me parse that a little bit.
I would say that they might or might not be moving in the right direction. So, I mean, first of all, it depends on for what purposes.
Mm-hmm.
So if you're thinking about this in terms of employment and so forth, and I need to build a practical system that solves a problem,
mm-hmm.
maybe you don't want to be so empiricist because you know some things about that problem. So if you're, building
the go forward could be reflected, and they built that in.
I think that's fine. The real problem, I think, is that, I think there's a couple. One is that people are kind of setting the wrong goal for themselves. So they're trying to minimize the innate component. Now, clearly, in this latest thing, they clarified what innate component is relevant there. That, I think, is good work.
Mm-hmm.
I think there needs to be more work like that across more problems, and people have to acknowledge that that's actually what's driving. So the paper is pitched as we got rid of human knowledge. What it should be is we used human knowledge to figure out the right stuff that's kind of the kernel that we need in order to solve the problem. And then we should go out and find more kernels that we need instead of starting with the prior that the number of kernels we need is 0. Which is kind of what Jan does.
Good. Well, I wish we had more time. Unfortunately, we are past time. So thanks very much, Gary. That was